picture of these CCD cameras all lined up, and they would use the gyroscopes to keep the telescope pointed just at that field of view for 3 years. So we could ask for continuous data for 3 years on any star that landed on one of these postage stamps. So that was really amazing data, and also very high precision. You don't have to worry about clouds. You don't have to worry about the sun rising and setting. So very, very, very good data, much better than anything we could do with a huge amount of labor and travel back in the 90s. So this is a picture of that CCD array, so you can see how big it is compared to the Worker before it was launched. And you can see them all right here. And here they've put it on the telescope, it's up in there, and they're mounting the third stage of the Kepler spacecraft onto the third stage of the rocket. And this is a close-up of the field of view. They aimed it at a certain place to get a lot of stars but not have too crowded of a field. But there were still over 13 million stars in this field of view. They were limited by computers and the amount of memory they had for collecting data. So only about 100,000 stars could be observed per quarter, per every 3 months. And you could request the expensive amount of data, the 1 minute cadence data, where you would get a data point every minute. Just imagine that. I could never do that by myself at the telescope. I would be having to move the telescope back and forth to comparison stars and guiding it. I wouldn't get enough light in 1 minute, but this telescope could do it. Or you can also take 30-minute longer cadence integrations for the fainter stars or stars that had a longer period. The one star that I did get some interesting data on was this one, Theta Sig, which was the brightest star that they let on the postage stamp pixels. The rest of them they tried to put in between because these stars saturated a lot of pixels and took resources away from other stars. So Kepler, as I said, was pointed in this field of view for a good reason. It was a place that was right next to a spiral arm of the Milky Way, so there were lots of stars, but not too many. Unfortunately, a lot of the stars that were in that field of view were faint, and they were far away, 600 to 3,000 light years away. So if you discovered a planet around one of those more distant stars, you wouldn't be able to visit it or even send a signal back and forth to it at light speed in our lifetime. So they're not as exciting maybe for people that are interested in planets. But in 2013, there were 4 gyroscopes in Kepler keeping it pointed. They had one extra that would keep it pointed at that place in the sky. But after the failure of the second, they only had 2 left, then they couldn't keep it pointed in that direction. And they had to instead use the sun as a third gyroscope and use photons, almost like a solar sail, keeping the spacecraft oriented as a third axis. So when they did that, they needed to start pointing the Kepler telescope in the opposite direction from the sun. So that meant lining it up on the ecliptic plane, which is the plane that the planets and the sun and the zodiac are going through in our sky. So they would move it every 3 months, and as the sun moved around and the Earth relative to it, and they would take data for 3 months on these different fields. So they did about 18 fields from 2013 to 2018, and you could propose stars in any one of these fields, and then we could look at much closer stars and many more stars because you weren't restricted to that 1.1 area of the sky. So this is a picture of how the solar radiation would be used in this angular these aluminum reflective areas in these solar panels that would catch the light. The photons would actually kind of keep it balanced. So this point here would have pressure here and here, and so it would keep it from rotating around in this direction. And the other 2 gyros that were still working would keep it in the other two directions. But they still needed to supplement that by some thruster firing every 6 hours to stabilize it. So eventually, the Kepler spacecraft did run out of fuel, and they had to turn it off. So I don't know if I have yeah, November 15th of 2018, they actually turned it off. So I wanted to show you why we put the spacecraft up and what they were doing with it a little bit more to give you a better feel. I don't know how many of you saw the Venus transit in 2012. Venus goes in front of the sun every so often, but it's every couple hundred years apart. There's pairs of these, a few years, 6 years or so apart. But this transit happened to be visible, and I'm sitting here in back of UNMLA with the telescope projecting Venus on the surface of the sun. This is a picture through the telescope, but I was also projecting it. So Venus is pretty visible. It's big, but it only blocks 0.0076% of the sun's light. So this is a transit in 2012 and one in 2004, just before that. Then just last year, some of you may have seen the Mercury transit. So this was, I observed this from Overlook Park, and I was putting my cell phone up toward the eyepiece to take a picture. And here's the picture of Mercury transiting the sun. So you see it's even tinier. It's 0.0012% of the sun's light. And this is a professional time-lapse picture of Mercury going in front. So what astronomers wanted to do is they wanted to observe a star continuously for a long, long time. The sun only goes around, the Earth only gets in front of the sun if it's in the right orientation exactly, as looked at from another star, only once a year. So you have to really look over many years to find an Earth-like planet, or even a closer by Mercury or Venus-like planet with a shorter period around one of these stars. And you would ideally like to see it go by a couple times. So, and you also need a very sensitive photometer to see just this tiny amount of light blocked out as the planet goes in front of the star. So that's what Kepler and now the TESS spacecraft main missions were. They were looking for planets in front of these stars. So sort of like this. This is a really big planet compared to this star. But you can see the flux change here of the photometer, and I think this is folded data from a planet going in front of a star. And you see it only goes up, changes by 0.01%. So it's really hard to pick this out. And they're still looking through the data today from Kepler and K2. And every time I look at their website, they find more planets and more candidates to confirm. They try to confirm them by other means, ground-based observations, additional data, data analysis, to several different techniques to confirm them. So right now, Kepler is up to 2,300 confirmed planets with about as many candidates. And it found about 30 small planets in the habitable zone, meaning the area where liquid water could exist on the planet. And it was also smaller, kind of like the Earth. The K2 mission, the one with looking at the different places around the ecliptic plane, found 410 confirmed planets so far and 889 candidates. And now the TESS mission, which has been going since 2018, has 67 confirmed planets and many, many more candidates. So a lot of amateur astronomers are working on the data, finding more candidates and also trying to confirm them. So Kepler, you would see lots of things in the news like this of the latest planet discovered by Kepler. This one was discovered a long time ago, but it had two Sunlike stars, two G-type stars like the sun, with a planet that was pretty big, about 1/8 the size of Jupiter, orbiting those two stars every 131 days. So they found lots of exotic systems like this with two suns or multiple giant planets and very close in, all kinds of really interesting planets. So I'm going to go into the part about the stars. I was interested in Kepler not because I wanted to find planets, although I think that's a really cool thing, and I'm glad they're doing it, and I would like to get more involved in it. But I was interested in the data on stars. And as I was going through my career, they would find more and more types of variable stars. And it seems like stars of nearly every type and nearly every evolution state are showing brightness variations, maybe very small, but still there, due to pulsations. So this picture is a picture of the luminosity of stars plotted against their temperature, with the hottest stars over here to the right. These are the red giant stars, and the hottest, the coolest stars, but the very large stars. And these are very small, but hot. These are going toward becoming white dwarfs, and these two are the white dwarf types that pulsate. And right in the middle here is something called the main sequence. And that's where stars spend a lot of their lifetime burning hydrogen into helium in their cores. And that is what the sun is doing today. So the sun on this picture is down here, and it's considered obviously a solar-like star. So all the stars like the pulsate like the sun are down in this yellow blob. So I worked on the sun for a long time, and there were quite a few unanswered questions about solar physics. And I thought, well, if we could just observe other sun-like stars or stars that are different from the sun, just a little bit different, maybe we could get some clues about what we might be doing wrong in our solar modeling and our physics to solve some of these problems. So I was very interested in the Gamma Doradus stars, which are a little bit hotter and a little bit more massive than the sun, and these things called the Delta Scooty stars, which are up here. They're again a little bit hotter, a little bit more massive. And if we have time at the end, I may even talk about these massive Btype stars, the Beta Cephei and the slowly pulsating B stars that were understood a little bit later, and they're about 5 to 20 times the mass of the sun. So the Gamma Dor and the Delta Scooty variable stars, like the sun, pulsate in lots of modes simultaneously. Delta Scooty stars are about twice the mass of the sun. They pulsate in acoustic modes or sound modes, and the periods of those are about 2 hours. If we compare with the sun's periods are about 5 minutes. So they're a lot longer period. It takes longer time to observe an entire pulsation cycle. So that makes it nicer to go to space to see that, to follow it for a long time. And the Gamma Dor stars are about 1.5 times the mass of the sun, and they pulsated in a different type of mode that we were never able to find in the sun. We think it's in there, but it just has too low an amplitude to see at the surface. And these are gravity modes, and they have periods of about 1 to 3 days, so that makes it really hard to follow a whole period on the Earth. Plus, if they're 1 day period, you're just getting 1 cycle per day aliases with the sun's rotation, so it makes it very hard to understand them. So this is just a zoom in of sort of that same diagram before with the Sunlike stars, the Gamma Dor stars, the Delta Scooty stars. And these dashed lines I may talk about a lot more. It's called the pulsation instability strip, or the region where Delta Scooty stars pulsate. And if we went way up here, they would be where the Cepheid variables are pulsating as well. So something we want to know more about is what's going on inside stars. And different types of stars around the mass of the sun, lower and higher, have a different interior structure. If a star is very low mass, half the mass of the sun, the star is convecting or boiling just fully all the way through the star. If it's like the sun, around 1/2 to 1.5 solar masses, the inside is not, it's radiative. That means the X-rays are just, the photons from the nuclear generation are just randomly walking out and diffusing out of the sun. Eventually they get out. It takes them like 10 million years, but they get out. And then out here, because it's more efficient, convection starts happening to carry the energy out in the outer 30% of the sun. So if you go up a little bit more massive, to the Gamma Dor stars, they're kind of right in between. They have convection in the core, and they have a convective envelope. And then if you go up to the Delta Scooty stars, like 2 solar mass stars, they have radiation in the envelope, just the photons coming out, very, very weak convective envelope, and a convective core. So we want to verify if our modeling, how big is this core, how much hydrogen is it mixing in. There are all kinds of questions that we have about other kinds of stars, and these other stars also tend to rotate more rapidly than the sun. So they have a lot of interesting phenomena that we'd like to understand. So the next few graphs, I'm going to try to explain more in analogy than in physics how stars pulsate. So the sun its modes do not continuously live. They get excited by convective cells, and then they damp out, and then other modes are excited and damped out. So the modes don't, they're not vibrating continuously. They're not staying driven. But in other kinds of stars, like the Gamma Dor and the Delta Scooty stars, the modes are very long-lived, and they are driven by a mechanism called the kappa effect inside the envelope of the star. And maybe well, I guess one analogy is, say you've just had a swing out here in the wind. If it's just randomly hit by the wind, it might start moving back and forth, and then it might stop, and then it might randomly move a little bit and stop. And that's kind of what the sun's surface is doing in its pulsating. But the other stars, what's going on is the outer envelope of the star is kind of like a person on a swing, and they are either pumping the swing themselves and getting to go higher and higher until there's some limit. And of course, there's a limit that this person will fall off, or go all the way around, or something bad will happen if they keep getting higher and higher amplitude. So there's a limit. And here's a case of a person being pushed by someone on the swing. And if you push at just the right time, and if you pump at just the right time, you can get the amplitude to get bigger and bigger. And there's always these two have a limit, because you don't want the kids to get hurt. But and with stars, what happens is they start losing energy at the outer part of their pulsation faster than they can then the pumping can provide it. So they have a limit as well. So what's going on with the Delta Scooty stars is that they are being driven by a layer inside the star. This is surface temperature and center temperature, where helium is ionizing. Helium has 2 electrons and 2 neutrons and 2 protons in the center. And when the radiation is trying to get out, this layer is just about at the right place to be pushing on the rest of the star to get it to pulsate. So energy is trying to get out, but it hits this higher opacity region, this region where helium is starting to ionize. So the energy, instead of going out, actually flings an electron off, and the energy goes into that electron, and the matter now has more pressure, and it's heating up. So that's what's making it expand outward. And then as that material expands outward, the helium electron goes back on, and it cools off, and it comes back down, and then it's back in place again to get another push, just like with the swing from the radiation that's going to knock the electron off again. So this helium bump is what's driving the Delta Scooty stars from the kappa effect mechanism. So there are more massive stars, the Myra variables, that pulsate with periods of like a year instead of a day, that are driven by the hydrogen ionization. And then there are stars like the Beta Cephei and SPB stars, those 5 to 20 solar mass stars, that are driven by this Z bump, which is where iron is, and other elements near iron are capturing photons and getting excited electrons and ionizing electrons. So different places in the envelope, if they're at just the right place in that type of star, they can provide the push to the outer layers. So I often show this picture when I'm talking about the sun. Whoops. This is a picture of just a bell. And this bell, if you ring it using the ringer with the chain, I guess is sitting there, it'll vibrate in several different modes, different overtones. And if you can get a high-speed camera, this thing called a Dopplergram here, where they're looking at the certain frequencies of vibration. You can see that there are node lines for this lower frequency mode. There are fewer node lines, and this is the lower overtone. And then there's an intermediate overtone. This picture is showing the different frequencies at 1,000 hertz, 1,400, and 2,600 hertz. And as you get more and more node lines, the frequency of that overtone gets higher and higher. So the sun is going in thousands of these different modes. You just ring it and it's got a whole bunch of overtones that are vibrating the surface in and out. And because we're so close to the sun, we can actually look at all these different modes and figure out what their frequencies are and identify them. So just like this picture, you see a whole bunch of different modes. L of 1 has 1 node line. L of 10 has 10 node lines on the surface. This is an L of 5 with 5 node lines. They can also go horizontally, like on that bell. But it's not just the surface of the sun that's ringing. The entire inside of the sun is participating in the vibration. I'm going to close my window 1 second. Hearing too much rain. Okay, so, which is great. First time I've heard rain in a long time. These modes actually vibrate all the way through the center of the sun. And by using different modes and trying to match their frequencies and doing some mathematical analysis, you can figure out all kinds of things about the inside of the sun. And that's a whole nother talk where we found the sound speed, the rotation rates, all kinds of things, and also found out that our physics isn't quite right. So it's very interesting. So I was thinking, well, okay, what other stars can we look at, as I said? So I wanted to try to look at these Gamma Dor and these Delta Scooty stars with the spacecraft observations, because their periods, these stars are far away. The periods aren't just 5 minutes where you can watch many periods in one day. Periods are 2 hours, 1 day, 3 days. So it's very hard to get data on them. So before Kepler, we did look at quite a few Delta Scooty stars. This GB means ground-based. We discovered many. We discovered many Gamma Dor stars, and we even discovered a few hybrid stars that pulsated in both types of modes, pressure and gravity modes. So these blue stars are the Gamma Dor stars, and these lines are where we expected them to be. Well, they're pretty close. They're a little bit off in temperature, but they're pretty close. And the Delta Scooty stars, and this is where we expected them to be between these two lines. And the few hybrids, well, they're not exactly at the overlap between the two, but they're pretty close. So we thought, well, we're doing pretty well. We almost understand these Delta Scooty and Gamma Dor and hybrid stars. So the year after Kepler was launched, we published actually a 2010 APJ letter, and then this paper in 2011, where we looked at a lot of Kepler stars. And these are the red again is the Delta Scooty stars. Well, they're kind of all over the place. They're even too cool to be too cold temperature to be Delta Scooty stars. We found a lot of Gamma Dor stars, and they were often way over here, too hot to be Gamma Dor stars. And here's the error bars. Some of this has been cleaned up by just observing the stars more and getting a better temperature, but not all of it. And the big surprise was these hybrid stars that pulsate in both types of modes. Those seem to be the most common, in fact, and they're everywhere on this diagram. They're not where they should be, right here between the Gamma Dor and the Delta Scooty range. They're just everywhere. So we had another problem to solve. How do we understand the pulsations of these and the content of these stars? So we're still working on that today. So I worked on Kepler until I still have data sitting on the Kepler spacecraft, and it'll come back in 60 years going around the same orbit as the Earth, and it'll kind of meet up with the Earth again, but I don't think they're going to get the data off of it. They've officially declared it retired. So, but fortunately, 6 months before that, we launched the TESS spacecraft. Now, its main mission was to look at transiting exoplanets also, this time around more nearby stars and cooler stars than the Kepler mission was looking at. And they are, the opportunities for observing stars are a little bit different. it only looked at continuously a target for 27 days if it was far from the pole of the Earth, the Earth's, the ecliptic pole. But if the star was near the ecliptic pole, the fields of view might overlap and you could look at it for up to 1 year. They also had a guest investigator program, and like TESS, or like Kepler, you could get data for 30 minutes cadence, and you could also get, for Kepler, you could get 1 minute. For TESS, you could get 2-minute cadence observations. So this is what the orbit of the TESS spacecraft is. I don't think I showed you, I meant to, the Kepler orbit. It's really all the way, it follows the Earth. It's in a trailing orbit from the Earth around the sun. But the TESS mission is closer to the Earth, but it's not in a place where the Earth is going to get in the way of the observing. So it was launched, it did a couple of lunar flybys, and then it went out in this elliptical orbit, tilted from the Earth-Moon orbit. You see here's the Moon orbit, and here's the Earth, and it's tilted. And every half lunar orbit, it makes a rendezvous every 13.7 days with the Moon to give it a little tug and keep it very stable in this blue orbit right here. So, and because it's far away from the Earth and it's looking out in some direction, it doesn't have the problem with the Earth getting in the way every day. So that's it's a nice feature, just like Kepler. And this is a picture of what its observing strategy is. So what they did is they started with the southern hemisphere, and they lined up these strips of the CCD cameras. There were 4 of them, not 35 in a postage stamp like Kepler. There were 4 of them, and they lined them up from the ecliptic pole to near the equator. And then every 27 days, they would rotate this strip around. So you see the stars that are near the top right here, they can get a whole 351 days of observing in this red area. In these other areas, they don't overlap as long, so those stars only get 189 days. And all the way down here to the stars that are near the ecliptic plane, they only get 27 days. So you can choose from any of these stars, but if you want a really long time series, the ones up by the pole are better. And so they spent 1 year looking at the southern hemisphere, and then they flipped it over the spacecraft and looked at the northern hemisphere. And now they've considered their main mission a success. They finished surveying all the stuff they were going to do. One of the disadvantages is they missed the ecliptic plane entirely. And remember I said that's where K2 was observing. So it would be nice to revisit some of those K2 stars with TESS, and that's probably what they're going to do in the future, because we couldn't get to them with this strategy. It just didn't quite cover the ecliptic plane. So this is another picture just showing you, this is the TESS ecliptic coordinates, but there's also the Earth coordinates. So this would be like the Earth's celestial rotation pole, and the Kepler ecliptic plane is offset by that, offset from that by the 23.5 degrees. So it doesn't quite line up with our equatorial coordinates. Okay, so this is maybe, well, this tells you what I have done this summer while I was working from home. Over a year ago, we proposed to use TESS to look at these A-type stars that are like delta Scooty stars, but they have peculiar abundances. They have underabundances of some elements, calcium, scandium, high abundances of titanium and other elements. And the abundance anomalies are thought to be caused by radiation pressure pushing some of the elements up, and settling, pulling some of the just gravitational settling or thermal diffusion pulling the elements down. And this settling was also expected to cause the helium that was responsible for that pulsation driving to settle out of that region so that they wouldn't pulsate. They would lose that opacity bump that the photons were pushing against to get it to pulsate. So these stars were not expected to pulsate. So we looked at a sample of stars that were very well observed for their abundances. They knew their temperature, their gravity very accurately, 62 stars. And we wanted to see if these stars pulsated or not. So why do they pulsate? Why do some of them pulsate and some not? I'm giving it away. They did find some that pulsate. How can they pulsate if the helium is settled out? Do we need some other explanation? So these are some of the questions we wanted to answer. So from this original 62 star sample, you can see that a lot of the stars lay in that delta Scooty region between those two lines in the instability strip. A couple of them were in the Gamma Dor region, and some were in that hybrid region. And there were a whole bunch over here that were outside of both. They were so hot, and we didn't expect those to be doing delta Scooty pulsations. So we looked at these stars. We started to with tests. And we were, as of this paper being written for a June conference, we had data on 21 stars. I think we have data now on 30 stars. And some of them weren't observed for one reason or another, priority of the spacecraft, for example. So out of these 21, all the ones that have these black dots are where they lie. If they have nothing by them, it means that they didn't pulsate. Well, that's good because they're AM stars. We weren't expecting them to pulsate. So a lot of them didn't pulsate. A lot of the ones up here, like we expected, they're outside of the instability strip, so they shouldn't be pulsating. But some of them did pulsate. We have 3 Gamma Dor stars here, and these are those stars that should be over here. They're way over here in this hot region. 2 of them are outside even the delta Scooty region. And then we found 2 hybrid candidates right here, these ones with H's, where they pulsate in both types of Gamma Dor and delta Scooty type pulsations, and they should be right here in this overlap region. Well, this one is, but this other one is way out of place. So the question is, why are these pulsating? I'd like to show you just a bunch of pictures now of the actual data from the spacecraft and some analysis, and this was all done by Jason Jakowitz at New Mexico. I'm going to get this wrong. New Mexico State in Las Cruces. So this is a picture of one of the stars that turned out to be a delta Scooty star. And you see it was observed during this sector 16 and 17. So these are those 27-day sector strips that I was telling you about. Well, it looks like a bunch of noise. If you zoom in on a 3-day zoom, you can see it going up and down really fast. And that period is kind of like a delta Scooty pulsation period between 5 and 20 cycles per day, so a couple of hours. So here we've made an amplitude spectrum, kind of like that spectrum of the bell. What are the frequencies that it's pulsating in? What are the frequencies that the star is vibrating in? And you can see it's vibrating in a whole bunch of different modes, a lot of different of those overtones that you might, like on the bell, just like on the bell I showed you. And we could look over more time and see if these same modes persist, or if they go away, or if some of them get higher in amplitude or in loudness, and some damp out. So this was one of the delta Scooty stars we found. This is one of the hybrid stars we found. So here you see the light curve. It's got some obvious pulsations. These are kind of spread, these big peaks are spread more further apart, more like 1-day periods. So you look over here in the amplitudes and you see a bunch of peaks. They're not very well resolved. We really need more data on this star. About 1 cycle per day, so 1-day period. And that's the Gamma Dor pulsations. And then you see a whole bunch over here of the delta Scooty pulsations. So this will be a great star to look at and try to find out what's going on. Why is the star vibrating in both types of modes? Here's another hybrid Gamma Dor delta Scooty candidate. It only has one really good Gamma Dor mode, and it might not even be a Gamma Dor mode, which is why I'm calling it a candidate. It could be a rotation period or some other period. And here are all the delta Scooty modes on this star. And here's 3 more Gamma Dor candidates. So these just have the low frequency pulsations, but they don't show anything in the delta Scooty frequency pulsations. Then there were some fun stars like this one I didn't expect. This is a binary, an eclipsing binary. And it supposedly has a gamma Dor component. One of the two stars is a gamma Dor, but you would have to subtract out these eclipses, which are alternating because one star is going in front of the other and then it's switching to figure out what's going on with the gamma Dor star. And maybe the binarity is actually responsible for the pulsations. So we have to work on that star more. And then there were these strange stars that were just pulsating in maybe one mode. It was varying in amplitude, very irregular, had maybe some other features like flares going on. We don't have any idea what these are. These could be stars with big star spots that are rotating, maybe 5 or 6 day period of rotation. They could be connected, two binary stars that are connected together basically and are rotating like a kind of a dumbbell around each other, or it could be some kind of pulsation. So we don't know what those are of those 21. So it's been very interesting to just look at these and try to, it gives you 20 lifetimes of work to try to understand what all these stars are doing. And then I want to close, I think, on one more spacecraft that I tried to use. And the final report was due on these stars today, actually. This is I have more work to do on them. Constellation satellites. These were launched by a consortium of Austria, Canada, and Poland. They're really tiny little satellites. They were built in Canada. And they are targeting the stars that Kepler didn't. And those were basically those bright stars. Remember I told you the bright stars that Kepler, they tried to keep them off the camera because they would just saturate all the pixels. So this is targeting those bright stars, less than 6th magnitude. And there were 6 satellites planned, but Bright Montreal didn't actually get off the upper rocket stage. So there's only 5 up in space, and they're deteriorating pretty rapidly. They're in Earth orbit, and the solar rays and cosmic rays are deteriorating these, and so I don't know how much longer they're going to be in operate. They'll operate, but the quality of the data is going down. So, and they're in low Earth orbit, as I said, between 600 and 800 kilometers elevation. So they can't look at any stars for continuously. What they do is they look at a particular field, and I asked for data in the original Kepler field because I wanted to follow up with stars we looked at from Kepler from 2009. I wanted to see what they're doing today with Bright. So we looked at them. You can look for up to 180 days, and you can just look at it for about 15 minutes during each orbit of Earth because the Earth is going to get in the way. So you don't get continuous data. And there are a lot of constraints about the range of the camera exposures, depends on the brightness. They have to make it very short exposure because these stars will saturate the cameras again if you stare at it for too long, like staring at the sun for more than a fraction of a second, just hurt your eyes. So they have them looking at B-type stars, these beta Cephei and SB stars. They're much more massive than the sun, and they're really bright too. A lot of them are brighter than many stars in the sky. So it made a lot of sense to look at them with the Bright spacecraft. And I'm not going to talk too much about their pulsations, but I looked at, this is the Kepler field of view again, so the stars I looked at were all in this Kepler field of view, but none of them even made it on this picture because they were 6th magnitude or fainter. This theta sig is 4.5 magnitudes. I think this picture stopped showing stars at 5th magnitude, but they were all in this field of view. And we did a lot of comparisons. I'm not going to go through these, but this is all in my paper, which I put on archive today with our analysis, and you can go read it if you'd like. We did a lot of comparison between the Bright data and the Kepler data, which I said we couldn't get it. I got some Kepler data. And the way that I got it was asking the director of Kepler for his director's discretionary time back in 2009. I asked him for a week of data, or maybe 90 days of data, or just something special, because I thought these stars would be special and would be worth wasting a lot of pixels on for a short amount of time. And the director, who was Martin Still at the time, actually took this data for us. So I could now compare it with the bright data and see what it's doing. And in some cases, I'm not going to look at these, that you see exactly the same thing you saw before between bright and TESS, but in some cases, between bright and TESS, or bright and Kepler, either one. In some cases, though, the TESS data was just not as good as the Kepler data was. Here's some Kepler data frequencies of one of those stars to see frequencies. So doing the comparison and maybe doing some more ground-based observing, we hope to write some more papers about these stars. So basically the bright data was fine, but it was lower signal to noise than Kepler. So if you could get Kepler data, it would have been better. And we can't do that anymore. Hopefully, maybe in the future, we can do some more of this. Okay, so I don't know if this paper is going to come out tomorrow, but I sent it to Archive today, and you should be able to find it with my name. If you want a copy of it, you can email me at joy@lanel.gov, and I would be happy to send it to you. It was given at an amateur astronomer conference, so it may not be very inaccessible to amateurs. It was meant to be something that amateur observers could read and understand. Okay, I am done. Any question?
Yeah, thanks a lot, Joyce. So at this point, if you have questions, please type them into the chat, and I will read them. I can start off with one from Galen, who asks, what are the pulsation amplitudes of the Delta Scooty and Gamma Dor stars?
Okay, well, the Delta Scooties can be several tenths of a magnitude. And some of them, like the one I just showed, if I can get back there, I don't know if I can. Are you still seeing my screen? You can see this one.
We still see it.
Yeah, these modes are 70 parts per million amplitude. So they're very low amplitude. You could not see these with the telescope on the ground. But there are Delta Scooty stars you can observe from your backyard. It takes a little bit bigger telescope. You want to do it for a tiny telescope. 6-inch, 10-inch, 12-inch telescope, you can take photometric data, CCD data on Delta Scooty stars and submit it to the AAVSO website, and professional astronomers will use it for their research. So there are some Delta Scooties that you can look at the pulsations. The Gamma Dors are harder. I looked at a really bright one for a long time at McDonald with the 30-inch telescope. And that was about the brightest one we could find. And it didn't vary very much. You couldn't see too much. So these are not the greatest star. They're of a lot of interest because they're nearby the sun in tight lines of the sun. So if you can understand them, you might understand the sun a little bit better. So and they pulsate in lots of modes. So if you can get all these modes, you get more information about the star. So they're of a lot of interest, but they're hard to observe from the ground.
On that note, so it sounds like the way that you would see it for the ones that you can see in your backyard, you really need like a camera. It's not like you can take a big amateur telescope and look and see it dim and brighten it with your naked eye.
You would have to look at it versus a comparison star over time, and then write it down, and then look at it over several hours. I think you could do a little bit with that way visually or with your telescope, but I would say a camera would be your best bet. And take exposures, all night, and then go back to your computer and process it. Then you would find it. But I haven't done that myself. So other people are more adept. This is what, I specialized more into going the last 20 years looking at these space-based observations, last 10 years, I guess. So I have never learned how to use cameras in my backyard to do it. I'd like to, but I haven't had time yet.
That sounds pretty cool. I imagine that maybe some of the people in the audience tonight are pretty good with cameras and their telescopes. Um,
There are, the AVSO has been doing a set of webinars every Saturday with different observing sections. And they just did one, short period variables, including the Scooty stars. And these are on YouTube. You can look at the AVSO website and see what different groups in the AVSO are observing from their backyard, basically, and how to do it. They're even going to provide tutorials and all kinds, and you could join their section and they'll help you learn how to do it. So I would recommend those. They've been doing those all summer because we couldn't, because of COVID, people weren't going to the conferences, were in person. We're showing up to do it in person.
oh, that's really awesome. I think I just found the website for that, and I sent it to everyone in the chat. So if you're looking at the chat, hopefully you can check that out. Okay, well, so as I wait for more questions to come in, I have a couple of my own, if you don't mind. One thing that sort of struck my fancy about your talk is the process of applying for time on these telescopes and for actually getting the data. Would you mind talking a little bit more about that? Like what's the experience like to use these space telescopes?
I've had a really good experience with each of these groups of people, Kepler, and Btype. You can, with Kepler and with TESS, they have a guest observer program, and about a year before the spacecraft starts scheduling its observations, you use their NASA or some other national website to apply. You put in a proposal and you have to make a target list. So you have to do your research on what stars are going to be visible and have a good motivation, scientific justification. And it gets reviewed by panels, just like at NASA reviews every other kind of proposal. And a lot of them, sort of the top ones, will actually get approved for some small money. So in the original Kepler mission, I had a couple of proposals get approved for a small amount of funding. And I was able to get that at the lab. But if you don't get the funding, every time I've requested stars, they've always scheduled them for observations and have done the observations and have sent them. And they'll either send me a link where I could download all the data at once, like they're doing on TESS, or I could go to the Mikulski Archive for Space Telescopes, where they've been archiving the data. And TESS and Kepler data are not proprietary. They are publicly available as soon as they get it, get the data processed. A lot of processing for you, so you don't have to do, worry about bad pixels and things that you might really not know enough to do because you're not an expert running the spacecraft in orbit. So it's been a really good experience. And the same is true with Bright. They were taking proposals, they would send you the data. Bright was giving a 1-year proprietary period, which for me ended today. And after that, my data will be public. They do the same kind of thing. And I think they're just going to make all the data public in the future because I don't think it's as good as it used to be with the deteriorating cameras. So if you're interested in doing this, I found it a really nice experience. Everyone was very helpful. And even if you don't get any funding, you usually get data. I have test data coming in right now on more of these AM stars and on some Cepheid variables.
Thanks for the explanation. A question from Rick. Can you infer some previously unknown physics in these stars or the sun from your satellite observations?
Oh, yeah. Well, one of the things that these massive B stars are telling us is that a lot of them are pulsating in hybrid modes too, pressure and gravity modes both. And with our pulsation models, the only way we can get those to pulsate is to have higher iron opacities. And coincidentally, higher opacities would help with a lot of our solar problems. So solar modeling problems. So if we can get a handle on how much opacity increase do we need, and then understand how to work with the atomic physicists and the experimentalists who measure opacities at the NIF experiment or at the Sandia Z experiment, and try to understand if our opacities could be incorrect, and we really need to have the higher ones. That's going to be a big advance, and it's going to affect all the types of stars, including the sun. It won't affect the Gamma Dor Delta Scooty as much, maybe, because they're pulsating, we think, because of helium, but we are starting to look for other driving pulsation mechanisms for these stars involving turbulent pressure and hydrogen and other, I don't know, maybe gravitational settling of iron into certain layers, although I've tried that and it doesn't really work. So we're looking for what really is causing the hybrid pulsations in the Delta Scooty and Gamma Dor stars. And we're learning about convection and how much of the star it really takes up by looking at these other stars. So there's a lot of physics questions we're interested in, yes.
I have a comment from Stephen Becker who said, very interesting talk, Joyce. So I agree.
Okay.
I think it was pretty cool.
I hope it wasn't, it was at least some of it was understandable to you all. If it is at too high a level, I'd be interested to know, because if I give a talk in the future, I would like the feedback. So any of you who are listening, please fill out the survey and let me know specifically what worked and what didn't and how I can improve it.
Yes, so if you want to give Joyce feedback, feel free to message, while the Zoom chat is running, feel free to message me. Otherwise, feel free to go on the website or email PEEC and let us know.
You will get a survey. You'll get a survey request.
Aha, okay.
Email. Yeah.
I didn't know that.
I think tomorrow, I think you'll get one tomorrow asking for feedback, so.
Cool. Well, please fill out the survey and make sure Joyce knows what you thought. And I had kind of a offhand question, which I'm not sure, maybe I missed it in your talk. Do you know where the names came from for Delta Scooty and Gamma Dor?
Oh, it's a good question. They usually name these stars after their prototype star, the first one discovered. So Gamma Dor, I think these are both more southern hemisphere constellations. Scooties is a constellation, and Delta is the fourth brightest star in that constellation because it goes by Alpha, Beta, Gamma, Delta. So it's named after that star that was discovered in the southern hemisphere sky in that constellation, Scooties. And there's another constellation, and it's another southern hemisphere one, so I don't even know how to pronounce it either. I think it's Doradus or Dorado. I'm not sure which. Steve Becker might be better at this. And Gamma is the third brightest star in that constellation. So they named them after the star that showed the where the pulsation type was first discovered. So, and in that constellation. So it makes me think that the Gamma Doradus star itself, if you were in the southern hemisphere, if you observed it, you might be able to see these oscillations much more easily than you could with some of the fainter ones.
Cool.
Yeah.
Okay. Well, we are reaching 8 o'clock here. So, and I don't see any more questions in the chat. So I guess now is the time to say thank you very much, Joyce, for sharing with us tonight. And everyone who's tuning in, please visit the PEEC website, peeknature.org/events for more talks like this one. Thanks again for tuning in, and everyone have a good night.
Okay, have a good night, everyone. Thanks again for listening.